Okay. Welcome everybody, sit down, and still coming into the room, join us. We are doing the PG Day Postgres track, and we're just good on time. So that's great. We're now at 11:30, and I'm gonna have a 40-minute presentation, I believe, yes, by Vladlen, Popolitov, if I got that right. So he works in the Laboratory of Advanced Development and Research, and his research focuses on vector indexes and vector databases, also a hot topic in the whole conversations around AI and Gen AI systems. So I'll hand it over to Vladlen. If we can give him a round of applause, please.
Hello, Sawadika, Ni hao, bonjour. Vector databases gained significant popularity in the recent years and became very popular in 2023. On this chart, you can see ANNbenchmark.com results in 2023, and Postgres with PG vector showed in the bottom line. It is slowest in the terms of queries per rate. By 2024, situation dramatically changed. Timescale DB published own benchmark. Authors used datasets with 50 million vectors, 700 dimensions, and as you can see, Postgres is 16 times faster and cost is by 75% lower. Now it's quite easy to change or to measure cost because we can buy service from cloud providers and can easily calculate cost. In 2025, VectorCourt.ai did benchmark for their extensions. They used dataset line with 100 million vectors, and the purpose of this benchmark was to demonstrate the showcase of linear scalability and performance reaching 10,000 queries per second, increasing number of workers on the server with 2 replicas and with 100 CPUs and 1 terabyte memory. They used this server from Amazon cloud. And they use algorithm based on inf, and they use bit quantization. For those of you who are unfamiliar with vector, it's a brief introductions to vector. The growing use of vectors started from development and implemented word vectors by programs Word2Vec and GLAV. GLAV means global vector. They represented vectors for words, and these vectors is a list of coordinates in n-dimensional space, and vectors can be manipulated such as added, subtracted. Since 2017, with rise of transformers models, applications started to calculate vectors for any types of data, not only for text, for images, audio, video, for sequences like data from sensors, air pressure, temperature, earthquake detectors. And now vectors used in many applications like anomaly detection, fraud detection, log files analysis, a lot of application. First important property of the vectors, vectors group concepts and meaning to similar clusters. For example, if we are talking about tower, word for word tower will be located in this vector space near the vectors of word building or skyscraper. Similarly, if you look at substances, for example, hydrogen, oxygen, metal, steel, or cities like Moscow, Bangkok, Tokyo, they would be clustered according to their meaning. And the second properties of vector, it was discovered later. Direction in the vector space corresponds to some meaning or concept. Let's take two words, man and woman, and find difference, this green vector. If we apply this difference to the word such as king, resulting vector will be near vector for word queen. It's not exactly the same because word queen has a lot of meaning. It's not only wife of a king. It can be name of chess piece king or musical band king, but it's in near location. Similarly, if we take word son and apply this vector, it will be near to the word daughter. It means that this green vector, it corresponds to the concept of gender. It's why vector so powerful. Vector can efficiently encode concepts and meanings as a mathematical objects. For example, concept, I show by my hand, concept animal, concept color brown, concept jumps, concept quick, and it's similar to vector fox. It's not exactly, but how it works. Why vector so powerful, we can use in many applications. And the more dimensions we have in this space, the more concept we can encode. And in the same time, the harder for computer to process, why we have a lot to do with them. I should mention PGVector is one of the mature extensions. It has two algorithms. First, in flat, it's simple, and HNSW, universal algorithm. It's used in many applications. I describe it in next slide. HNSW, it has first parameter is m, number of numbers for every vector. It's a graph-based algorithm, and graph means that every vector has neighbors. During index creation, every object added to the index and placed to the layer. The more number of the layer, the less object on this layer. Its quantity decreased exponentially and power the same number m. For example, if we have data set 1 million vectors, on the zero level we have all million vectors, while on the first level will be 20 times less, in our example 20 I took, it will be 50,000. On the second level, 20 times less than on the first level, and so on. And entry point of this graph structure will be always on the highest level. when we start search, we always start from the entry point, taking all neighbors and identifying vector nearest to the lookup vector. We, from this point, trying to find numbers of all of these lookup vectors. When we found nearest neighbor, we go to the lower level. It has 20 times more vector, and we continue this process and find nearest vector, and so on. We go step by step to the lowest vector, and here we already approached in the neighborhood of our lookup vector. It means highest level help to solve problem of big and fast steps, while lowest levels solve problem of small and precise steps. It's why this algorithm is so powerful. And when we have to stop this search, it's a chart of tried neighbors with distance, with measured distance. When we continue the search, we found local minimums during the search and count number of neighbors in every minimum. We have second parameter, EF. For example, if it's 30, we do not stop here because here we have less than 30, and we stop here because we have enough neighbors. Even if we continue search further somewhere, probably we can find closer vectors, but we need to stop to balance accuracy and query rate. How these parameters influence speed and accuracy? During construction phase, M and EF, the higher value increase accuracy, but index build process is slower. They helps to make index with better quality. And M decrease search rate because index is bigger, and EF, slower, faster. It makes faster. It's mistakes here. Makes faster because index has better quality. And during search process, if EF higher, then accuracy is higher because we considered more neighbors and found more closest neighbors, but search rate later because we processed more data. It's demonstrated on this graph. And we go further. From database point of view, vector is a usual data type. After creation of extension in the vector, we can declare table with a column of vector data types. And when we have vectors in our code, it's represented as a list of numbers enclosed in square brackets, the same as vector presented in Python. When we make lookup in database, we use a EF search parameter. It's EF parameter I told before. We set it to value, and algorithm return up to this value. In this case, up to 100 nearest neighbor. In query, we use order by value and distance operator, Euclidean or angular distance, and limit result to desired number, for example, 10 in this case. This method has one drawback, it was from description of this algorithm in the original article. It's never return more than 100 records. We'll speak later about this. As I said before, Postgres started to compete with other vector databases, and one of the methods to increase query rate is reduce vector size. Usual vector has element float 4, it's float number. We can replace it with float 2 and reduce size of vector by half. This approach allows us to make it without converting original data. We can convert data during index process and create index with half-vec data, but original data remains the same. And we need to convert query making cast to half-vec type. I show benchmark result also later. And if we can increase query rate by reducing size, can we take it further and reduce size to 1 bit? It's intriguing. How we can do? If element is greater than 0, we set it to 1. If it's less or equal to 0, we set it to 0. It's reduced memory requirements by factor 32. And it was shown that it works good if vector has dimensions more than 1,000 elements. And in any case, we have to check our data set because some data sets can have property, for example, of elements are positive, and it will not work. It should be checked for every data set. This method is supported by pgvector and pgvector scale. Explain it visual slide. We change elements to 0, 1 for one axis and 0, 1 for other axis. It became 0, 0, 1, 0, 1, 1, and 1, 0. The distance of distance between element in one cluster equals to 0. Distance to nearby elements equal to 1, and distance to more distant cluster increases as distance to cluster also increases. This type of distance is known as a Hamming distance. It's counted as a count of position where value differs. Here value the same. Here value differs in one position, and here in more position. In this example, in 2 position. When we create bit quantized index, we also doesn't need to convert our original data. We can encode them only in the index. We use a function, for example, binary quantize, and field with vector converts to binary representation. And we also need to change query vector. And here we have 2 options. First option is ordinary options, as I show it with half-vec. We add binary quantize function. But this method will result in lower accuracy because we lost precision during this quantization. And we have second option. We can make search in two steps. We convert query to select from subquery. In subquery, we search for 800, it's example, 800 elements using approximate bit search. And then in outer query, we calculate exact distance, order by exact distance, and limit result to desired number. I show result in benchmark. This table compiled from benchmark demonstrated by Jonathan Katz. He took dataset ZIFT, GIST, DBpedia with 1 million vectors, dimensions 1, 9, 1500s. And you see table size increased according to dataset size. Index size for vector approximately linear. For half-vec, it's reduced by half. And for bit index, it's reduced by 20 times. It's not 32 because index has graph structure and overhead with free spaces, but it's also great. And here is a numeric result. Let's look at half-vec results. Size reduced, amount of information decreased, but accuracy remain on the good level comparing to vector. It's not worse. Result for bit is interesting. For small dimensions, it's poor. Bit quantization should not be used for such data sets. And here is the long data sets, and it's also poor result due to quality of, due to nature of data in these data sets. But for data sets with 1,000+ dimensions, you can see that it's option 1 search without re-rank. It's also not ideal, but I hope you see. But for search with re-rank, it's two-step search, latency time is less than vector, you can see, and quality also on reasonable level. It means that for bit quantization can be used for very large databases, reducing index size by 20 times. Index can be accessed quickly and even stored in cache, in shared buffers, further enhancing performance. However, if you start to make even very simple application, you will face situations that you don't need simply nearest neighbors. You need nearest neighbors filtered by some criteria. For example, you need documents with some language code or files created before some date or after some date, or images bigger or smaller. And when you apply this filter to the query, it can happen that this query will not return any result because EF search constant limited the quantity of returned candidates. It's not good because index is designed to accelerate query, not to alter the behavior. To address this issue, we must know the properties of our data sets and the properties of filter values. Is the list of these values fixed, or is it depends on user Is it small, as small as 2.5 values, or as big as 1,000 values? I would explain two important properties of datasets. First is the selectivity. Selectivity is the fraction of points returned by predicate. On the top picture, it's the high selectivity, 50%. You see here data sets corresponding to 2 predicates, and lower selectivity if we have more predicates. And second important property of data sets, it's a correlation, how vectors distribute in the space and this predicate distribute in the space. Upper picture, no correlation, predicates distributed uniformly in the space. Here is a positive correlation. Green vectors clustered to one cluster, blue clustered to other cluster, and here is a lookup vector. It's located inside of cluster where we look, and negative correlation also to clusters, and lookup vector located in around of vectors with other type of predicates. It's important because some algorithms work good with no correlation situation, but stop working in a situation with positive correlation and especially with negative correlation. On this table, I would like to summarize how to query works with different selectivity. One moment. As selectivity drops, quantity of distinct values in the filter increased. Query received less correct values, and in the situation where 1,000 distinct values, this index became useless. And when rows in the table grows, situation became even worse because query time grows as a logarithmic function. And in this situation, vector index stopped working. It can be a situation when we have a lot of distinct values, and in this case, we can use the usual B3 index that can work in this situation. What's the solution? First, partial index. If we have fixed number of predicates, we can create partial index with the same clause as in select, and it will work in this partial case. Second, streaming or iterative scan, it's algorithm that continue return rows until they found all needed rows according to this predicate. It was introduced in previous year in PGVector in this version, and it's in PGVector scale was by default. You create index and it's always work. And I already said when regular B3 index is fast, when we have a lot of different values and every combination corresponds to small quantity of vectors, we can try to use B3 index. Multi-column index. Multi-column index can filter predicates before search, and it can solve all problems with selectivity and correlation effectively. And there is a problem now. In open source, there is no one implementation in open source. For example, Postgres Pro has extension, but it's available only to licensed clients. It's how it works. After creation of extension, we can create index including all fields that we need to filter, and then include it to query. And it takes all graphs needed for these clauses and prepare result already. Here is a table with summarizing. Regular index, it's drop accuracy when selectivity drops, more distinct values. Streaming vector index, it work good with no filter, then drops query rate linearly. And multi-column vector index, it works opposite. When selectivity increased and quality of search and rate remains on the high level, and slower only for less or greater operators. Here you can see in the table or in the chart, quality of the regular search drops, its record drops, and on the lower selectivity it became useless. Its streaming index, it has good accuracy but worse query per second, and multi-column index has much more performance. It's not implementation question, it's a difference in nature of this algorithm. And in small selectivity, streaming has very low performance, and multi-index has very high performance and became as dot here. Here are recommendations. I simply read them. I stay in presentation. You can read if you're interested. And some conclusions. Postgres allows to store large amount of vector data, and in the same time we can use advantages of database as standard API, backup, user management, replication. Postgres now has many extensions in open source. It's possible to control vector types, and it has many index formats. We can choose for our task. And in performance, Postgres now is compatible to vector databases, and while retaining all advantages of databases. And also it has challenges. Still need to improve support for multi-column index. It should be much more multi-column index, the same as Postgres now has for different application, different index, B3 for one situation, GIST for other situation, and GIN for special situation for this. And also improve cost estimation procedures for vector index. Now it's not implemented in smart way. It only return cost, one cost for all situation. It will not help you if you have two vector index in one column. It should be improved. It's all. Question, please.
Thank you for your report. It was very interesting. I have a question. As far as I understand, Postgres still keeps everything in heap tables and in regular indexes and in vol. So exactly we have for about 3 copies of the same data. one for backup, maybe we can say that we have two copies because we still have it in index and in the heap table. As far as I understand, actually this data usually is not changing, so we don't need MVCC, and exactly keeping in heap looks like an overhead. Maybe there are some optimizations, maybe in your fork, or maybe they are planned to keep it only in index for non-multiversal concurrency control versions, but for something stable, you put some kind of a file, and after that you can just connect, like for the where, with Postgres and to read from it. Thanks.
First questions about copies. It's really, we have copy of vector in heap table. It's copy of vector in index and in backup. But bit-quantized index store only decreased version of this index. It's already plus. And regarding about this overhead, I haven't heard that there is some project about storing in other format. Because as I know, our clients, big shops, for example, they store 100 millions of vector and they update them in the process of their work, and update, and in the same time, for example, every 6 hours then send 6 million requests to get nearest neighbors from these big data sets. They work and they write and read in the same time to update information about goods and about their clients. It's no.
I'm curious why have like a set of like discrete numbers of like vectors for like different like size. Why not have like a more like dynamic one where like, let's say this like particular data point has like maybe 501 vectors, another one may have like 15 vectors or something like that, where it's like more dynamic and more numbers in between, and maybe like each like point or each number in the vector can represent more things.
You mean numbers inside of vectors?
Yeah.
If I correctly understood your questions, really we can deal with vectors. We don't know what's inside of these vectors. It's calculated by model. It's we almost never know what's inside. And
I mean like the number of numbers within the vectors.
It depends on the model. Model originally designed to prepare vectors of specific lengths. It can be designed to make it shorter to be faster, or longer to have more information inside, and it will be slower, and it depends on models on after of this model. If it has 512, we deal with this length, if I correctly understood you. But I can.
So I have a question about indexing. Now, in terms generally, I assume it's mostly GIST and SP-GIST. Which of these two, sort of, where do you see the trade-offs between GIST and SP-GIST for creating your vector indexes?
You mean performance of creating indexes?
As far as what are the trade-offs of the different index types? I assume they're mostly going to be GIST and SP-GIST, but if you use other types, love to hear about that too.
HNSW requires much more calculation efforts, and usually when algorithm written, it works with data set storing in memory. As soon as part of data go to the index, creation time dramatically increases by 100 times in my calculation. And it's two methods to solve it. One of the bit quantization to prepare smallest index. And other approach we used in our company, for example, to split index by clusters. And as soon as memory filled, we stored cluster to the disk and start to build new cluster. And then we need additional procedure to look between these clusters. It's a second approach. It's not written in the articles, by the way, if it's an idea for some of you. And okay.
Okay, that was a great presentation. So thank you very much for that insight on vectors in Postgres. Can we give a round of applause, please? Thank you.